In this video we look at the concept of power, and the power developed by a force is simply the rate at which the force does work. If we've got a constant force F acting in the same direction as the displacement, we know that the work done is equal to F times S. So the power, which is the rate of doing work, is the derivative of the work with respect to time. So we've got to do the derivative of Fs with respect to time. F is a constant, so we can pull that outside the differentiation. So we've got the power is F times ds by dt, but ds by dt is the rate of change of the displacement, which is precisely the velocity. So we've got the power developed by a force is equal to the force times by the velocity, if the force is acting in the same direction as the motion. The SI unit of power is the watt, which is a rate of working of 1 joule per second, and that's named after James Watt, who was one of the founding fathers of the Industrial Revolution. The formula P equals F times V is valid whenever the force acts in the same direction as the motion. Proving that requires a little bit beyond the scope of this video, and perhaps your teacher will be able to give you an explanation of why that's the case. However, we will use this formula P equals F times V in our examples later in this video. So let's move to the first example. We've got a vehicle of mass 800 kilograms travelling on horizontal ground at v meters per second. Experiences a resisting force which is proportional to the vehicle's speed. When the vehicle is working at a rate of 144 kilowatts, the maximum speed of the vehicle is 30 meters per second. We've got to determine the acceleration of the vehicle when it's working at a rate of 100 kilowatts and travelling with speed 20 meters per second. And we're also going to work out the power output of the vehicle if it's travelling at a constant speed of 99 kilometers per hour. So we'll start by drawing a diagram. So we've got our vehicle travelling on a horizontal ground. We'll suppose it's got a speed of v meters per second and an acceleration of a meters per second squared. The forces acting on the vehicle are the driving force D, produced by the vehicle, and the resistive forces, which we're going to just call RF at the moment. There is, of course, the weight of the vehicle acting vertically downwards, and the normal reaction from the ground acting through the four wheels, acting vertically upwards. Since everything in this question is happening horizontally, though, we can ignore those forces at this stage. We know that the resistive force is proportional to the vehicle's speed, so that's telling me that the resistive force must equal a constant times V. We know that the power output of a vehicle travelling in a straight line with speed v meters per second, whose engine is producing a propulsive or driving force of d newtons, is given by P equals D times V. That's just our P equals FV result from the previous page. If P equals dV, we can rewrite that to give D equals P over V. So now, applying Newton's second law to the right, we have D minus RF must equal M times A. In other words, we've got P over V minus KV must equal the mass of the vehicle, 800 times by A. And this is going to be the key equation for answering the whole of this question. So, we know that when the vehicle is working at a rate of 144 kilowatts, the maximum speed of the vehicle is 30 meters per second. So, if I put V equals 30 and P equals 144,000, now be careful, we must express P in watts. We've been told the vehicle has a power of 144 kilowatts, so that means that P is 144,000. So when V is 30 and P is 144,000, the vehicle is travelling at its maximum speed, so there is no acceleration. So I've got 144,000 divided by 30 minus 30k must equal 0. Multiply that by 30, that gives me 144,000 equals 900k, so k is 160. For part 1 of the equation now, we know that P is now 100,000 and that the vehicle is travelling with speed 20 meters per second. So we've got P is 100,000, we've got V is 20, and we've got K is 160. So equation 1, the P over V minus KV equals 800A equation, now becomes 100,000 divided by 20, take away 160 times by 20 equals 800A. And that very rapidly gives me A equals 2.25 meters per second squared. Moving on to the second part of the question. If the vehicle is moving at a constant speed of 99 kilometers per hour, we must first of all turn this into SI units. So 99 kilometers per hour is 99,000 meters per hour. But 1 hour is 3,600 seconds. So we've got 99 times by 1,000 divided by 3,600, which gives me a speed of 27.5 meters per second. So returning again to equation 1, we've got P over V minus KV equals 800A. We know that A is 0 because the vehicle is moving at a constant speed. So therefore we have got P divided by 27.5, take away 160 times by 27.5 must equal 0, which gives me P is 121,000 watts, or equivalently 121 kilowatts. Moving to a second example, we have a vehicle of mass 800 kilograms travelling up a road inclined at 8 degrees to the horizontal at V meters per second. Experiences a resisting force of 160 V newtons. We've got to determine the maximum speed of the vehicle as it goes up the hill if its engine is working at a rate of 144 kilowatts. And then secondly, we have to determine the acceleration of the vehicle when it's travelling up the hill with a speed of 20 meters per second and working at a rate of 144 kilowatts. So we'll start by drawing a diagram. So there's the van going up the slope. We need to put all of the forces onto the diagram, and this time we must put all of the forces on because the slope, the vehicle is not moving in just a horizontal direction. Okay, so we've got the driving force, we have the weight, we have the resistive forces, and we've got the normal reaction. Applying Newton's second law up the slope, we have, first of all, the driving force, D, acting up the slope. Then we've got the component of the weight acting down the slope. So that's going to give me D minus, now the component of the weight acting down the slope is 800g sine 8, minus the resistive force, which also is acting down the slope, and the resistive force is 160v. So my resultant force is D minus 800g sine 8 minus 160v, must equal the mass 800 times by the acceleration a. Now we know that throughout this question that the power output of the van is 144,000 watts. So we've got the power 144,000 must equal D times V. So D must be 144,000 divided by V. So our equation that we're going to be using throughout this question is going to be 144,000 divided by V minus 800g sine 8 minus 160v equals 800a. If the car is going at its maximum speed up the slope, that tells me that the acceleration is 0. So I've got the equation 144,000 over v minus 800g sine 8 minus 160v equals 0. Multiplying up by v gives me 144,000 minus 800g sine 8 times v minus 160v squared equals 0. So we've got a quadratic equation for v. That quadratic equation for v can be solved using a calculator, and we obtain the solutions v equals 26.8 or minus 33.6. The minus 33.6 case is clearly not appropriate. We can't have a maximum speed up the slope which actually is a speed down the slope, so we'll ignore that one. So our maximum speed up the slope is 26.8 meters per second. Moving on to part B, where we have to determine the acceleration of the vehicle when it's travelling up the hill with a speed of 20 meters per second and working at a rate of 144 kilowatts. We return to our first equation, 144,000 over v minus 800g sine 8 minus 160v equals 800a. Insert v equals 20 into this. So we've got 144,000 over 20 minus 800g sine 8 minus 160 times 20 must equal 800a. Work out the left hand side. 2,908.9 equals 800a. So a is 3.64 meters per second squared. So to finish the video, here are a couple of questions to have a go at, which use very similar techniques to the examples that we've just looked at. So pause the video, have a go at these two questions. And when you've had a go at these two questions, we've actually come to the end of this video.